Dear friends and colleagues, my name is Oleg Cojocari. I'm CEO and co-founder of ACST GmbH in Germany. First of all, I would like to send my greetings to Optical Society of Korea and to delegates of Optical and Photonics Congress. Also, I would like to express my deep gratefulness to organizers of this conference and of this session in particular for the courage to organize such an event in such an unpredictable time. My presentation is entitled Schottky Diode based high power, high efficiency 500 GHz source and applications. ACST has been founded in 2006 with main goal of providing European scientific community with Schottky diodes for TerGas applications. This was the first European supplier of such component and the second worldwide after VDI and USA. ACST was a spin-off company from Technical University in Darmstadt in Germany. We continue work in the university laboratories until 2013, when the team started to grow and we needed particular facilities for our further development. So we moved in 2013 to open facilities to Hanau, which is just about 50 kilometers from Darmstadt, and we continue working and on various R&D projects of European Space Agency and industrial applications until in 2017, 2020, when we becomes to develop subsystems and systems like TerGas sources, frequency extenders for vector network analyzers, and front ends for FMCW radars. The ACST facility in Hanau is placed about 35 kilometers from Frankfurt, the main airport, so it's very central, easy to get. So please, you can visit us anyway, anytime. It has a little bit about 300 square meters of clean room facility for development and fabrication, and another about 300 square meters for offices. Concerning ACST core competency, I would like to mention here the Schottky diodes fabrication and high power multiplier technology for frequency up conversion. Of course, as a result of this are high power and wideband millimeter submillimeter wave sources as a main product of ACST. But of course, we can do frequency extenders like vector network analyzer extenders, signal generator extenders, and some other customer products. Of course, we have a large space heritage due to the several space missions, space projects with the European Space Agency and our other space agencies from different countries. And we, reliability tests and for space qualification and commercial qualifications. Thank you. This slide shows, so based on this technology, high power multiplier technology, ACST developed a range of different sources up to 500 gigahertz at the moment. So these sources are separated in two big categories. One category is high power sources, which are relatively narrow band. So as I told, the bandwidth is usually about 15% of high power sources. And for full band sources, which have full waveguide band, but of course the efficiency and output power is lower. So that means that's why you see here two categories of high power and full band sources, which differ. So the full band sources are about 10 dB, have about 10 dB lower power than the high power versions. I have to mention here that this kind of output power performance, this performance is compared well with state of the art worldwide. So the full band sources are really comparably with state of the art, but narrow band and high power versions, I think, are unprecedented if we consider not only the output power but also the bandwidth. Then I do not know other suppliers which can produce this performance. Okay, there are some research and development entities like JPL, which can provide this performance, but they are not commercial. They are particularly laboratory of NASA, and they do not sell these components. The SCST is a commercial company, and SCST sells these components for real applications and scientific instrumentation. SCST products are used for different applications, for terahertz generation and detection, for terahertz spectroscopy, for millimeter wave imaging, and different areas like scientific research, laboratory instrumentation, industry, security, and space. And our activity is distributed worldwide. So you see here the bottom picture show worldwide distribution of SCST products. It is clear. So this technology is currently emerging worldwide, and such a company like SCST with their products are requested by different customers worldwide. Let's go now to the main topic of this presentation. It is a 475 to 525 gigahertz source. Yeah, it's just one of the SCST sources. I just want to mention this in the title, that as a topic, but in fact the discussion here is all generally of high power sources. So they are usually modular sources. Here you see here the on-bench version, and right bottom picture is an on-bench version of the 500 gigahertz source, which show here the voltage control oscillator unit, VCO unit, followed by a W-band source, so AMC, and then followed by a high power amplifier, and then we have attenuator in the between, and then we have two doublers and 500 gigahertz horn antenna at the end for radiation of terahertz terahertz signals. The PSU, the power supply unit, is a separate unit connected by cables, and yeah, this is the outer view of on-bench system for on-bench version of the 500 GHz source. On the bottom left graph, you can see the performance. I'm sorry. The output power is about mostly about between 5 and 13 dBm, and the frequency range from 470 to 540 gigahertz. I want to say that here we still have some troubles with HPA. So the HPA is, as I told, it's high power amplifier MMIC. I usually procured externally, and this MMIC does not often, sometimes does not do not work as expected, and provide less power. And if they provide less power, the passive amplifiers, passive multipliers do not perform as required, as expected. That's why we have some dips here. For instance, at 510 gigahertz, some drops, and at about 495 gigahertz, a drop also. Yeah, these are not expected by simulations, and we are still working on these issues to improve this. So in fact, the problem is only the, as I told, just to improve the output power and flatness of the high power amplifiers on E band and W band. This slide shows another version of 500 GHz source, which is customized. So, you know, there are companies which already start to commercialize, to industrialize terahertz technology, and if they have, for instance, a system where they need a terahertz source, then this source have to be somehow mechanically integrated in these systems, and that's why in this case we got mechanical restrictions from the customer. They told, for instance, they need a source which it is like 20 times 15 centimeters and 10 centimeters high and so on, and has to provide such power and so on, and that's why we applied particular effort to mechanically design and realize such a source. You see here even there are some heat sinks to cool down the system and so on. So that was a particular development project for a particular customer. And you see here the output power of a 20 milliwatt peak, which is great. So if you see the bandwidth from 475 to 525 gigahertz, and output power up to 20 milliwatt peak, I think this is nearly factor 10 more than other suppliers of such components, such systems. So again, this is this really state of the art in the world. But why we need such sources? So of course, these sources are usually used for laboratory instrumentation, for scientific research and so on. But I would like to say that recently, in the last several years appeared already terahertz cameras which are based on microbolometer, room temperature microbolometers, which in fact are were developed for infrared radiation, but there are some companies which develop these infrared bolometers down to work efficiently, to work in terahertz range. And one of these developers is INO. It is a Canadian research institute. They developed a terahertz camera, which yeah, it has, I think, 300 times 400 pixels, something like that. It's really a lot of big array of microbolometers, and they are sensitive to terahertz radiation. So that means you can use this camera just like a normal video camera, but seeing terahertz radiation. That's great. It is a real-time video. It's a real-time imaging. You can do pictures, or you can do just videos using this camera. That's really great, and this offers a lot of perspective for development of terahertz, also for application of terahertz technology in industry. But the only problem with this camera is that this microbolometer arrays is not sensitive enough to detect the natural terahertz radiation. So that means they need a source, a light source in terahertz range. Just like like usual optical camera, they cannot see anything in darkness, and they need some illumination in order to see something, to make an imaging. Exactly the same situation is here, and for illumination, for terahertz illumination, we need these sources, and that's exactly the point of application of terahertz sources from ACST. Terahertz sources of ACST are large bandwidth and powerful, and are perfect terahertz illumination sources for this camera. And these two components together are offer a huge future for applications in terahertz and in industrial applications. In this case, we have, so the imaging, terahertz imaging can be done either in reflection mode, like usual, but they can also can be done also in transmission mode. This slide show the reflection mode, how it's done like, and if you go to the next slide, we see the results of this kind of imaging. So on the top picture you see optical picture, optical view of phone cell phone, which covered with a plastic cover, and in the bottom pictures on the left you see a terahertz picture done with a source of about 300 gigahertz, and on the right side bottom you see a comparative picture done of the same phone with at about 500 gigahertz. You see the difference. Of course, at 500 gigahertz, the resolution of the picture is much higher. You better see different details, but not only this. You see also there are some different effects which appear at different frequencies. So that means if you see here at the features at 300 GHz and 500 GHz are slightly different. There are some features at 300 GHz which are not seen at 500 GHz, and inversely. So that means there are some effects which still have to be investigated and considered for real applications. But nevertheless, this shows that this technology is able to see, to provide real-time images of objects hidden objects. So the next picture is similar, done with the same system by Eno in Canada. It shows just some scissors. On the left side bottom you see the 300 GHz image, and the right side 500 GHz image. It's obviously that plastic feature in this case are better seen at 300 GHz and practically are transparent at 500 GHz. That explains every material have some particularly absorbance lines and transparency lines, and it looks that this particular plastic have more reflectancy at 300 GHz than at 500 GHz. That's why at 500 GHz we see the metal inside the plastic, and even see here some screws which cannot be seen at 300 GHz. So again, shows that it's not only the resolution between of wavelengths, but also between of spectral properties of materials. So that's very interesting experiments, and these results have to be they are still under investigations to optimize our imaging systems in terahertz range. So another company which use in fact similar camera from a microbolometer array camera. Its company is called RaySecure, and they commercialize a scanner, envelope scanner for post. Just you see here scanner. It's just on the left hand side. This a box which has something inside, and you cannot see what is inside, but through the terahertz imaging you can see what is inside. And the RaySecure also brings some comparison to X-ray. I find this comparison very fair. The X-ray is already more than 100 years old. Yes, it's very famous, and it's particularly used for many for airport scanning of luggage. But the X-ray has a very high energy, and it is damaging it's harmful. It's harmful for radiation for human body. In contrast, the terahertz radiation is safe. It is not ionizing, and it is safe for human body. Okay, I also see here static 2D pictures for X-ray and real-time 3D video. I'm not sure what RaySecure means about, but okay, I trust them. Yeah, and of course, the terahertz system can be used by a relatively simple technician, and which does not need particular training for X-ray systems and so on. yeah, concerning the resolution, well, if Resecure claim this, then okay, but I cannot comment this. If you go to next slide, it shows there is a series of experiments performed by Resecure to compare the imaging provided by a system with about 300 gigahertz and a system source, in fact, performed at about 500 gigahertz. In fact, the system is the same. The only difference is the source. So the 300 gigahertz source, in this case, you see here it's about 200, around 282 gigahertz, and with about 10 milliwatts peak power. And another source which is around 500 gigahertz with about 20 milliwatt peak power. This source is from ACST. And let's us show look on the experiment results. This picture shows a gun in a box. You see here clearly how it looks at 500 gigahertz and how it looks at 300 gigahertz. Of course, the resolution is much better at 500 gigahertz than at 300 gigahertz. And this image is in transmission mode, not in reflection mode as we saw before from Eno, but it's in transmission mode. And you see that the resolution is of course at higher frequency is better, which is in fact as expected. The next slide shows the same experiment but with a knife and a bolster and also a box. You see here, of course, the holes, and it's obviously the resolution is better at 500 gigahertz, and you see these under different angles, which is also important for real life imaging system. The next slide shows some powder, which is obviously the same. In fact, it's nothing new. Of course, at 500 gigahertz the resolution is better, and you see also here that it's powder and not something else. This helps a lot to when you are going to scan the letters, for instance, envelope of letters. You can see either there is some particular foreign powders or liquids or any other objects in the envelope. And the next picture is same, just with liquids. So you see here how the liquids are inside of this envelope using terahertz imaging. Okay, if you want to know more about these applications, you can just look on homepage of Resecure. I think there is it's well enough described the applications and how it works. So to the conclusions, I would like to say that ACST in Germany is one of the leading supplier of terahertz sources worldwide, and we continue working on this kind of products and hope to become a leading supplier. Yes, for any applications like scientific instrumentation, for space application, and for real-life industrial applications. Thank you very much for your attention, and have a nice day.